I want you to, I gotta have your place. Okay, so this concept of net forces is probably one of the most important, like, big picture things that you've got to get. So we'll kind of go through the theory today, got an assignment on that, and then we'll start 3 straight labs that do nothing but reinforce this idea of net forces, okay? So it's one of the most vital concepts that you have to know. So, since you all are horrible at reading, this is a story that I wrote that kind of explains it. And it's kind of set in a medieval time frame. So I'm going to read this in a horrible British / Australian Scottish accent. Okay? There is going to be one audience participation line, and that's in the 3rd paragraph. Okay, you got that. You got this. Those of you who have one audience participation, don't screw it up.
Oh, I don't want to do that. Natalie, you gotta give it
I don't care. Okay? I don't care. Okay, anyway. Once upon a time in the kingdom of physician, there were 2 opposing forces. One represented the forward-looking people who wanted progress and were very positive. The other was the faction that opposed everything that the positive people wanted and were generally considered to be negative. Thus, in the kingdom, there was always a struggle between the 2 forces. The positive people had a variety of tools they applied in their battle. They would push up, lift, throw, hurl, heave. And once they discovered mechanized equipment, they started using rocket engines and hot air balloons. Theirs was viewed as a positive force since they were trying to move the kingdom forward. In opposition to such forward-thinking endeavors, there were the negative people who opposed anything the positive people would attempt, and they were negative. Boo. That was horrible. That was absolutely. We're going to try that again. In opposition to such forward-thinking endeavors, there were the negative people who opposed anything the positive people would attempt, and they were negative. Nice. As with the positive people, they too had various tools at their disposal. They were limited to only 2 tools, friction and gravity. The friction and gravity were generally referred to as the opposing forces and took away from the endeavors of the forces applied by the positive people. In future years, they would become known as the gravity and frictional mafia. The negative forces could also only be used in special circumstances. If the positive people were trying to move something horizontally, then the negative people would use friction to oppose the applied force. The more friction there was, the less positive force remained. AKA, the more money had to be paid out to the frictional mafia. The positive people were trying to get something into the air, like this balloon. Then the negative people would use the weight calculated by taking mass and gravitational acceleration. The more massive the object, the more money paid out to the gravity mafia. As is true of every epic battle, protocol had to be established to determine who won or lost each battle. After much wailing and gnashing of teeth, it was determined that a mathematical system would be established that force net equals force applied plus force opposing. Okay, that was a lot. All right, so here's how this plays out. I want to work with both systems. So here I've got a hydrogen-filled balloon, right? So if I take this, I hate helium-filled balloons. That's a whole other tirade I'll go off on later. So, I hate helium-filled balloons. If I was king, I would ban helium-filled balloons.
How did you get the hydrogen?
I have got a source. Yes.
What would happen if you put that in your mouth?
We'll light it when we get done.
Lighting is what I'm scared of.
Yeah. We'll fire it up when we get done because you need to see how hydrogen reacts with oxygen for rocket engines tomorrow. Okay. All right. It's just fun. It never gets old. Okay. So here's what I've got. So let me put a smaller binder clip on there. Let's go small. So I'm going to put the small binder clip on here, like so. Okay, and I let go of it, and I get a pretty decent acceleration upward. So at this point, here's the balloon, and it has some applied force created by the buoyancy of the hydrogen, which is lighter than air. Okay? So then, pulling down on it is the gravity mafia pulling down on the little binder clip. Okay? Technically, it's also pulling down in the balloon, but that's just going to muddy the waters. Let's just focus on this. So clearly, which one is bigger? The applied force going up or the gravitational force going down? Applied force going up. That's the direction of the acceleration. If I throw it down, it's like gravity in reverse. It's kind of cool. Oh, look, gravity in reverse. Oh, boom, goes back up. Okay, so your net force, this is why you have to learn vectors before you learn anything else. So then my net force is going to point from the origin up. So my applied force going up is bigger than my gravitational force acting down. I would strongly encourage you to get into the habit of drawing a chart that lists applied force, opposing force, and net force. Now, for now, I don't care about the numbers. We'll deal with the numbers later. This is just a conceptual idea. So we're going to define up as being a positive number. So there's some applied force that's acting upward. Gravity is pulling down on the binder clip, okay? So that's some negative number which is smaller than the applied force. So what's the sign of my net force?
Cancels out.
No, it's a positive number, okay? Which is why it accelerates upward, okay?
My bad.
It's okay. Now, listen to me very, 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 very carefully. It is net force. Speaking of unbalanced forces, it is,
I feel we should use that as a
that's okay.
budget corridor.
No one saw that happen, okay? Absolutely no one. That, I promise that will not be brought up at your 10-year reunion, ever, okay? No one will ever speak of that again. Okay, so, it is only net force, and net force only, that equals mass times acceleration. It isn't force friction, it isn't force applied, none of it. It's only net force that equals mass times acceleration. Now, might the net force just be friction? Yes. Might the net force just be gravity? Yes. Okay? But it is only net force that equals mass times acceleration. So, interesting thing happens. If I were to calculate this acceleration, I would have some positive net force divided by a small mass, because I don't have much mass here, to get the acceleration. Cool. Now, I'm going to swap out the smaller binder clip for a little bit bigger binder clip. Okay? Now when I let go of it, do I still get a positive net force?
Yes.
Yes. So now, this situation was with the Whittle binder clip. Okay? Now we're going to go with the same balloon. When I put the bigger binder clip on it, did that change the force in the balloon? No. It's still the exact same applied force because it's still the exact same balloon. Okay? So the applied force, if you set up a chart, again, which I highly recommend, my force applied is the exact same positive number. Okay? It's the exact same applied force. I haven't done anything differently. But what's happened to my opposing force now that I put that bigger binder clip on there?
Force negative got bigger.
Ah, now I have a bigger force working against it. I have to pay more money to the gravity mafia. Okay? So this has become it's still a negative number, but now it's a little bit bigger than what it was, because now I have more stuff, right? Gravity's pulling down on it harder. So is my net force still a positive number?
Yes, but less.
And I know that. because of the fact that I let go of it, it accelerates upward. But but what's happened to the value of my net force? Okay? So that's a small positive net force. Now, an interesting thing happens on the way to mathematics. Here's what I want you to look at. I'm going to have a positive net force that's smaller than what it was when I had the binder clip on. So I have a smaller net force. So not only do I have a smaller net force, but what's happened to the mass of the system? It's increased. So now I'm going to be dividing by a bigger mass. So when I divide by a bigger mass, all right, now visualize this. I have a smaller net force, but I'm going to be dividing by a bigger mass. So what's going to happen to my acceleration?
Smaller acceleration.
Now I'm either going to have a smaller acceleration. So when you go to launch rocket engines, okay, Apollo missions, whatever you want to do, when you look at getting a rocket off the ground, let's say that the rocket weighs 50 newtons, just a big number. That's the gravitational force acting down on the rocket engines. So what does your applied force have to be bigger than?
50.
50. It might be 51. It might be 52. I just have to have a force acting upward from my applied force that's bigger than what I have to pay to the gravity mafia, so that I end up with a positive net force. My net force doesn't have to be bigger than my opposing force. Only my applied force has to be bigger so that I can generate a net force. So this is where this becomes problematic in terms of mass. If you increase the mass of the rocket, it becomes a double whammy. Because not only are you weighing more, so now you have a bigger force to get up in the air, because you have to overcome more gravity, but then you shrink your net force, and then you're dividing that by a bigger mass, and then you even get a smaller acceleration. So this is why when they were building, like especially the Apollo missions to try to get to the moon, they had entire teams of engineers that did nothing but try and cut the weight of the ship. Because for every kilogram of mass they could reduce, that was a huge deal. Because then, that left us more positive net force. That created a bigger acceleration from the engines that we had. Okay. Now, if I put a second paper clip on here and let go of it, now what happens?
It drops.
It drops. Why?
Force negative is greater than the.
Yeah, so which one's bigger? My applied force going up or my gravitational force acting down? Gravitational force acting down. So I still have the exact same applied force. But what have I done to my opposing force?
Add more mass.
Made it bigger because I've added more mass. So now my net force is pointing in which direction?
Down.
Downward. So this is like gravity in slow motion. So when I drop it, it slows, right? If I throw it up, comes to a stop, comes back down. Now, if I take this back off, hydrogen is a very, very small molecule. So right now, when I let go of it, over a period of time, what's going to happen is that the hydrogen, even though that balloon looks solid, the hydrogen is actually escaping out of the balloon because the hydrogen is actually smaller than the pores in the balloon. So over a period of time, actually, I'm going to lose some, I'm going to let that go up. But I'm going to lose some hydrogen, and eventually, this thing is just going to hover, okay, because I'm going to lose some hydrogen. Now, when that thing just hovers, which we're pretty close to at this point, when it just hovers, what do you know about the two forces?
Cancel out.
They're going to cancel each other out. So I'm still going to have an upward force, but that's going to balance out the downward force. So gravity and applied force is the vertical version of friction and pushing something horizontally, okay? So if the forces add up to equal to 0, hey, there's forces, everything just balances out. So the other way that you can do this, and the application of this is a helicopter. So people go, why do you teach physics? Because I can go to Dr. Botts and say, I need a helicopter. Why? Because I'm teaching forces. Cool. Yeah.
Funding.
So But if I'm a math teacher and I ask for a helicopter, they're gonna go, you don't need a helicopter, here's a calculator. Cool, that's exciting. So, because I teach math with toys, I can get helicopters. So, we take off, okay? Now, at that point, where it just hovers, are there forces acting on the helicopter?
Yes.
Absolutely, but they all add up to zero. Now, if I want the helicopter to accelerate upward, I'm going to give a little bit. My battery's running down. Bingo, there we go. So, when it's hovering, does that mean there's no forces acting on it?
None of those forces.
No, it just means that all the forces add up to zero. Now, when I take off, open up that battery. Okay, now, at that point where it just took off, what do you know about the upward force
Greater force applied.
relative to the downward force?
Greater.
It's bigger, right? So this is why a lot of times you'll see these problems referred to as elevator problems, because they usually involve a helicopter or an elevator. Okay? So elevators work the same way. I'm guessing most of you have been on an elevator at some point in your life. Okay? So you walk into an elevator and you're standing there. Okay? If you want to accelerate upward, what has to happen? What does your applied force have to be greater than?
The gravity.
Yeah. So your force applied has to be bigger than your gravitational force acting down on you. What's the direction of your net force? Upward. Okay, cool. Right? Now, eventually, the elevator reaches a constant velocity. At the point where the elevator reaches a constant velocity, what do you know about the forces?
Can't see.
They're adding up to equal to zero. Now, you get to the 10th floor, what do you need to do? Speed up or slow down?
Slow down.
You need to slow down. So, when you go to slow down, guess what? Your applied force becomes less than your gravitational force, and you slow down to a stop. Okay? So, all an elevator does is work off the idea that force applied plus force opposing equals force net. That's it. That's all an elevator does. If you fly a helicopter, you better understand this concept. Now, so here's how it plays out in terms of rockets. So here I've got Robbie the rocket. And it has a mass of, I don't know, 5.0, no, 2.04 kilograms, okay? And the force of the rocket engines is 50 newtons. So, here's what you've got. Here's the rocket sitting on the launch pad, mass is 2.04 kilograms. The force of the rocket engines is 50 newtons. I want you to calculate the acceleration of the rocket engine. Now, here's what you're going to do wrong. And you sit there and you go, Mr. Burkamp, we won't do that. You lie. Okay? You're going to go, oh, physics is easy. Here's my force of 50 newtons. I'm going to divide that by 2.04 kilograms, and I'm going to get my acceleration. Okay? Bad. Who did you not pay off? The mafia. Which, gravity or friction? Gravity. You did not pay off the gravity mafia. Gravity mafia is not going to be happy at this point. Now remember, if you want to think of it monetarily, the gravity mafia charges $9.80 newtons per kilogram. Okay, that's the rate. So if I have 2.04 kilograms, how can I figure out how much I have to pay to the gravity mafia?
9.8 times 2.4.
9.8 times 2.04, what do you get?
Like 14 something. Oh wait. I don't know. The answer is 4.5.
That's,
I don't know. Just,
20.0.
yeah, 20.0. Okay? So, this is how much money you have to pay to the gravity mafia. Okay? So here's an analogy. Let's say Olivia is down in the lunchroom. And some little freshman comes up and says, hey, Olivia, kind of down on my luck, don't have any lunch money right now, but I'm hungry. Olivia goes, hey, you got a nice watch. I'll pay you $20 for the watch. Okay, so she pays $20 for the watch. She comes in the room. Jackson sees the watch. Goes, Olivia, that's a nice watch. Olivia goes, I'll sell it to you for $50. Jackson goes, fair deal. So Jackson pays Olivia $50. She paid $20 for the watch. What's her net profit? $30. Same thing is going to happen here. You have $50 to launch your space business, but you have to pay $20 of it for protection money to the mafia. How much money do you have left? $30. Now, so you can view this graphically. If I said, hey, draw vectors showing all the forces acting on the system. You got an upward force of 50. You got a downward force of negative 20 newtons, which is your gravitational force. So the difference between those two is your net force, which would be 30 newtons. Cool. Now, here's the other way that you can view this. If you're into charts, which I highly recommend charts on this deal, you're going to have force applied, force opposing, and force net. So in this situation, my applied force is 50 newtons. My opposing force is that negative 20 newtons. I end up with a net force of positive 30 newtons. Okay? Which value do I divide by mass to get the acceleration? The 50, the 20, or the 30? Only the 30. It is only the net force that equals mass times acceleration. So somebody take the 30 newtons and divide that by 2.04 kilograms. 14 something.
14.7.
0.7 meters per second squared. How would that number relate to your velocity time graph? Oh, there we are. We're pretty much in equilibrium. Nice.
I'm gonna go behind you.
Okay. So in your velocity time graph, that would be that slope 14.7 meters per second squared. Now, at that point, after some point in time, I'm going to shut off the rocket engines. If I shut off the rocket engines,
So we're having so much fun back here.
I got that. It's just fun. So,
It's
nice
like
applied
physics
force.
volleyball.
It is. So, if I shut off the rocket engines, or if I pop the balloon, which I'm not, I'm going to blow it up. But if I pop the balloon, or I shut off the rocket engines, what's the only force left acting on it?
Gravity.
Gravity. Then what becomes your net force?
The
Oh, the negative 20 newtons. So if I shut off the rocket engines, that's like me throwing this ball up in the air. And I promise you, if you shut off the rocket engines, this chart now becomes force applied, force opposing, force net. If I shut off the rocket engines, what's the value of my applied force? 0. What's the value of my opposing force? Negative 20 newtons. So what's my net force? Negative 20 newtons. Okay? Now, if I take the negative 20 newtons and divide that by the mass of 2.04 kilograms, what do you think we're going to get for the acceleration?
Oh, shouldn't we use gravity?
Yeah. Oh, guess what? The acceleration is going to be negative 9.8 meters per second squared.
Then all that adds up.
So, when you shut off the rocket engines right there, what's your graph going to do?
Go down.
Yeah, your graph is going to slope down like this, with the slope of negative 9.8 meters per second squared. Think you'll see a problem like that on the test?
Yeah.
Absolutely. Absolutely. Promise you. Absolutely, you're gonna see a problem like that on test. Now, the cool thing about hydrogen, Jackson said, there's some pretty good balloon out there.
It's flammable.
Yeah, so hydrogen will react with oxygen in here. So, on Friday, we did the methyl alcohol and oxygen, right? We got a nice flame, it went shooting across. Hydrogen and oxygen react as well. So, quick flashback to your days in chemistry. What do you get from the synthesis of hydrogen and oxygen? Water. Okay? Why do you get water and not hydrogen peroxide? Hydrogen peroxide makes sense. Oh, it's H2O2. Why don't we get hydrogen peroxide?
It's not as stable.
Yeah, Mother Nature's lazy creeping on, and Mother Nature goes, dude, hydrogen peroxide. It's just a lie. Mother Nature prefers water. If Mother Nature preferred hydrogen peroxide, our oceans would be full of hydrogen peroxide. Okay? Or it would be bad. It's like, oh, but if you got a cut, oh, just go swim in the ocean. So, you know, clear yourself right up. But it makes some water. So we're going to make some water. Now, conveniently, much like with methyl alcohol and the oxygen, you have to have what we call activation energy. You have to start the process. If hydrogen and oxygen spontaneously combusted to produce water, as those hydrogen molecules drifted out, they would spontaneously, you would see little flashes of light every time a hydrogen molecule ran into an oxygen molecule. Which would be cool, is like, oh, hey, let's just put some hydrogen in a balloon and just watch the hydrogen react with the oxygen, okay? Thankfully, that doesn't happen spontaneously, or literally, you would see these millions of little flashes of light around the balloon every time a hydrogen ran into an oxygen. So, we'll do this. So, hold this. Wake up. So, you want the lights on or off?
Off.
Okay, catch the lights.
How long have you been
Hit the bottom.
Smile
Okay. All right, so lift that up a little bit higher. Okay, here we go. 3, 2, 1. Oh, it even made the banjo ring. Okay. So, what? You thought what? Turn the light back on.
Bird camp, is that the Hindenburg 2.0?
Basically, yeah, but there were some other contributing factors to that. So, okay. So, obviously, in addition to water, what else did you get? Heat. Okay? You got a lot of heat. So basically what happened is that the hydrogen and oxygen were at the top of the roller coaster.
Bird camp's gonna get some eat.
And then all I did was push that hydrogen and oxygen over the top of the roller coaster, and then we went down like this. We ended up at water, okay? But in the process, we had to get rid of a lot of energy. That's what you all heard as sound and saw the flash of light. You felt that as heat. So going down the hill was just like people going, wah! As they go down the roller coaster, that's what you're doing, wah! That was going down the roller coaster. Okay, turn the lights back on.
You should do that again.
No. No.
Bird camp, where do you buy your hydrogen?
Huh?
Where do you buy your hydrogen? Asking for a friend.
I've got a big high pressure container of it.
Good enough.
Yeah, no. Okay. So, now let's talk friction.
What would, if that was helium, would it have done the same?
Oh, no. Helium wouldn't have done anything.
Boring.
Well, but here's what chemistry tries to answer.
Oh, makes sense.
How many electrons does helium have?
2.
2, right? Helium has 2 electrons and it has 2 St. Bernards. 2 protons, 2 chihuahuas, okay? Hydrogen is diatomic, right? it has 2 hydrogen atoms, so there's 2 protons, and it has 2 chihuahuas, right? So helium has 2 protons and 2 electrons, and it doesn't react. Hydrogen has 2 protons and 2 electrons, and it reacts violently with oxygen. Same number of particles, 2 chihuahuas, 2 St. Bernards. One produces a violent reaction, the other one doesn't. And that's what chemistry tries to answer, is that how can the arrangement of the chihuahuas produce a violent reaction in one and produce a completely noble gas in the other with the exact same number of particles? That's what chemistry tries to answer. Okay, so let's talk about friction. So if I take this cart, which is pretty frictionless, and I give it a push, right, I'm going to get a pretty big acceleration. But if I flip it over and I give it the same push, not a lot happens. What's the difference? Friction. It's the frictional mafia. So in horizontal motion, it's the same idea. I'm going to have some force applied. What could possibly work in the opposite direction? Force friction. Now, is gravity pulling down on it? Absolutely. Is there still force normal? Absolutely. But I don't care, because that doesn't impact the horizontal motion. So here's as simple as some problems can get. If it's a frictionless surface, like the wheels are down, I apply a force of 10 newtons. This thing has a mass of 1.02 kilograms, which if you multiply that by G, trust me, you get 10 newtons. So weighs negative 10 newtons, and the upward force normal is 10 newtons. So if I apply a force of 10 newtons, no, let me change that. I'm going to make that 5 newtons. I'm going to apply a force of 5 newtons to a 1.02 kilogram mass, and there's no friction. Okay? It's the same idea. You just go, oh, okay. Force applied, force opposing, force net. So if I don't give you any information about the frictional force, and I tell you that that force is 5 newtons, and you don't know anything about the friction, your net force is 5 newtons. Okay? That would, Olivia won't do this, but that would be like Olivia going to the freshman and going, hey, give me your watch. Okay. And the freshman just gives her her watch. Okay? Like I said, she won't do this. Okay, in my story, you're a good person. So you walk into the room and you saw that watch. You didn't give the freshman any money, but you saw the watch to Jackson for $5. How much money did you make? Because you don't have any cost against it. Okay? Now, in reality, let's say that there is friction. Let's say that I tell you that mu is actually 0.10. If mu is 0.1 and the force normal is 10 newtons, what's the force friction?
0.1. Oh, sorry, 1. Yeah, 0.1 times 10. Yeah. I didn't see the point. No, I know the equation.
Because force friction equals mu times force normal, right?
Yeah.
Same, nothing new, it's the same thing. So if I take 0.1 times 10 newtons, I get 1 newton. So if I apply 5 newtons of force, and the force friction is negative 1 newton, because that's in the opposite direction, so we'll make that negative. What's my net force?
4 newtons.
4 newtons. What's going to happen to the acceleration once there's friction? It's going to become less, because I have to use some of that force to pay off the frictional mafia. Now, what if I wanted, knowing that the frictional force is negative 1, if I wanted to push the block at a constant velocity, how much force would I have to apply? 1 newton. Okay? Got it? Good? Great. Okay, stop yonder.
Question.
Yes.
What did the
What
balloons
is all
float
this
everywhere?
like stuff that's on our papers?
Oh, God only knows, it might have come from the explosion. It's nothing radioactive, I don't think.
I don't think.
Oh,
You guys should be okay.